Today I will present you the project I've been working the last year on. So we have multiple presentations that that we're talking about Deep-SDM and where we can use them and where they were strong or not. And here I wanted to present you a project where we wanted to use Deep-SDM to improve microclimate modelization. So the microclimate and the difference with macroclimate is that macroclimate represents the climate over a region. It's generally like, for example, the above ground temperature, the precipitation, things like that, like the CHELSA variables. And microclimates represent the real conditions where organisms live. So it really depends, the variable that will matter depends on the organism you are looking at and the scale of the organism. So for example, ground worms or grasshoppers or mammals will have different conditions they live in. And so microclimate is the general word to describe the true condition. So for example, the temperature they live in, because the temperature at 5 centimeters above ground can be really different than the temperature at 2 meters above ground. So that's the difference between macro and microclimate. And so microclimate can represent a lot of different variables, and there are a lot of studies about different things that we can include in microclimate. Here we will mostly focus on the modelization of near ground temperature, so mostly the 5 centimeters above ground temperature. And so the problem with microclimate is that if you want to have data, you need to put loggers, and a lot of loggers to have, like, for example, your temperature. You have to go somewhere and put a logger and register over a long time all your temperature variability, for example, and that's a lot of data that you need. And so at the moment, most of the microclimate studies are quite relatively small in scale or are very specific to some kind of vegetation cover or kind of habitat because of the data requirement. And in this project, we wanted to see if we can make some useful use of species information to try to complete some of the information that you can have with the logger. Because the idea is that the species observation are linked to microclimate, because species live in some kind of microclimate. That also means that when you observe some species, you can have some clue about the microclimate where the species lives. And so we wanted to try some approach to use the species observation information to try to increase the amount of information you have about the microclimate for modelization. And for some species, some links are very strong with microclimate, for example, with tree and forest. So the tree is shading the forest, and so the story temperature is really different than the canopy temperature and things like that. So by selecting some species, we can probably get some very useful information about microclimate condition. And so one main advantage of this is that so this is the soil temp dataset. For temperature of microclimate is the biggest dataset, and there is like a few thousand of logger register. But in comparison, only if we take plant observation from the JBI, from iNaturalist and PlantNet, we have multiple million of them. And so we can bring way more data points and way more information if we can make interesting use of this information. And so this species observation, in addition to be numerous, they are also easy to use because you just need the species you observed and where you observed it, and you can do a lot with that. And there are a lot of spatial coverage, and as we know, they are in somehow linked to microclimate. And so here is the question, how we can use this species observation to include them in a microclimate modelization. And so it's here that we came to the idea to use Deep-SDM for multiple reasons. So the first reason is that we know that these models have some good performances. They are able to handle, if you use some kind of image model, they are able to handle some spatially explicit information like the spatial structure that could be very interesting for microclimate, for example, for the topography, where the topography will have a huge impact on the temperature. They easily integrate some high-resolution remote sensing data, and the main point is that they are encoders. So you can learn some variables that are a kind of latent variables by training a model on some tasks, so for example, species distribution, and then you can reuse some of the encoding you've learned to another task. And that's the idea why we wanted to use Deep-SDM for this task. So here is a very schematic view of a Deep-SDM. So we can use different data as input. So we will use Chelsea bioclim and some high-resolution remote sensing data, so for elevation and sentinel imagery. And then you learn the model to predict the distribution of multiple species at the same time. And by doing that, you learn a function that transforms your input to some feature space that is an encoding of your input that is way smaller. And the information that is retained inside should be the information useful to predict your species. And as we think the species are linked to microclimate, if the information is useful to predict the species, we hope that this information is also useful to predict the microclimate. So here it's just an example of why we think it could work. So that's from another study. Here it's a representation of a free latent variable space made by a Deep-SDM model. And we can see that spatially we can achieve with remote sensing imagery, we can achieve to encode some information that seems to be quite well linked to some landscape features. And so that was the plan, to use this encoding and then try to add another layer of model to predict the microclimate. So the idea is that we train the species distribution model, we reuse the encoding that the species distribution model learned, and we had the daily temperature from macroclimate, some other elevation information, and also we added the canopy height because we know that it's really highly correlated to near ground temperature. And this canopy height is also coming from another deep learning model on Sentinel that predict the vegetation height. And at the end, we use a regressor model that will predict the temperature. And we model that on, First, the question is which species you want to use for training the model and to capture the information you want. So there is no real good answer to this question. There are a lot of possibilities you can try. What we choose is to use only plant species for the simplicity, because first you have a lot of observation of plants and you know that they don't move. So it's quite easy to use them as when you try to make fine resolution mapping. And we also know that they are highly correlated to some microclimate information. So the study we wanted to try this approach is in Switzerland. So we have two datasets. We have the dataset of temperature loggers. So here is just temperature loggers that have been pulled in the field and that recorded the temperature over a year. And we have extracted plant observation from iNaturalist and PlantNet on Switzerland. And so we want to try this approach on this model. So the comparison for our model, we have two models to compare with. So on the right, we have a state-of-the-art that is called radiative transfer model that is half correlative, half mechanistic. So the idea is that they were computing some mechanistic approach to have a radiation estimate. So the radiation will be linked to the energy that goes to the ground. So it's a mechanistic approach. But then they were using a linear model to correlate that to the output of their mechanistic model and other factors like the macroclimate as well. And we also wanted to compare our model with a similar approach, but without the species, the deep species model inputs. So the idea is to reuse the same variable as daily Chelsea climate, elevation, and canopy height, and not using the encoded variable from the deep species model. And we can try multiple things, but in fact, when the metric we were trying to predict, they are quite close to linear correlation with this input variable, so we can try to simply make a linear model over this variable. And so here are the results. So the radiative transfer model, the results are copied from the paper, and there is a slight difference in the evaluation, so we can look at the range, and our goal was to have a similar range because we don't target the same exact precision with our method, because our method is more designed to be available globally. But so we want it to be not far in performances. And then the blue and green model are the model with the Deep-SDM approach and the linear model. So what we can see is that both the Deep-SDM based model and the linear model, they were performing quite close to the state-of-the-art radiative transfer model. And then what we also observed is that the linear model was every time better than the Deep-SDM based model. So we tried multiple things for the Deep-SDM based, changing the encoder, the number of latent variables, the regressor that we use at the end, but the result is always the same. The most performant model, if you want to use the Chelsea daily variable and things like that, is always the linear model. That was quite interesting, so we tested it after having done a lot of experiments, so it was a bit surprising that at the end only a simple linear model was working. So the fact that I didn't mention that, but the fact that the relationship can be linear is not, it's because we don't predict directly the temperature, but we are predicting the daily max, mean, and mean. And so this is mostly linearly correlate to the input variable. So that was interesting, and we were thinking, so if our variable were completely useless or not. Another thing we wanted to see if it's what it does look if you plot some maps. So here is the map of the maximum daily 5 centimeter above ground temperature of a random day in May 2021, somewhere in Switzerland. And what we can see is that the conclusion is a bit the same with the map, is that the linear model on the right was at least as good as the Deep-SDM based model that we have on the left. So we are not as precise at the state of the art because they were using very precise weather record from Switzerland and other variables that are at few meter resolution, where we were targeting more 10, 30 meter resolution. But the linear model seems to be pretty good. And in fact, the conclusion we have is that the number of sensors that we have, the 100 sensors that we have in the study, was not really enough to try to model with some encoded variable that are only spatial, because as soon as you want to make this prediction, you have only 100 spatial points, and you can very, very easily overfit over your point, and that's a thing we observed, that we can more overfit with all other variables, including the latent variable we tried. And as the output of the microclimate near ground temperature seems to be very decently linearly correlated to the input variable that we have, in fact, the linear model is the one that overfit the less and that generalizes the most. But one interesting thing is still that this model was not tried before, because people in microclimate are more into mechanistic model, and they don't really like the correlative approach. But the linear model we tried was using a canopy height model that is from Sentinel data, where you can compute the vegetation height. And that was a bit the same idea that we have, but this model really extract one meaningful variable instead of what we were doing with trying to encode some variable that we don't really know what is inside. The canopy height is clear, the variable. So it's a bit the same idea, but with a very clear information of what you would put. And so for the next step, what we were thinking is to continue on exploring this thing, but using the Ellenberg indicator value. So if instead of trying to encode some variable and to have information encoded, we want to try to just make a deep species distribution model at high resolution, and then with the species output, we can have some information about the preference of the species about the microclimate, and then model this preference and see if here we can have a more robust approach, because this information is more easily correlated to the microclimate. We also want to move from temperature to soil moisture, because in fact temperature we see with this linear model and the error we have that we are quite close to the ground truth, and that there is not so much room for improvement, or at least it doesn't seem to be very interesting to go deeper in that way. And another variable that is still very interesting is the soil moisture, where here you don't even have like the equivalent of macro climate temperature for soil moisture. The dataset for soil moisture is really more sparse, and so we want to try also on this other variable. Yeah. Thank you for your attention.
Thank you very much, Benjamin. So we have time for one or two questions. Is there any clarification requested?
Yes, for the Deep-SDM model, so you use PlantNet and iNaturalist data, so which are biased by sampling effort and detection bias. So maybe your feeder space also more capture the probability that the user is here, and not only the plants. And so maybe this could also be a reason why this variable is biased towards the prediction, or?
Yeah, that was a question we have, and we wanted to see that, and we have other dataset available in Switzerland. But the region where we have the sensor also put the loggers of temperature are some region where we have some points of observation of species. So we know that at least we have some representativeness of this environment where we have the ground truth. So we were not sure about if it's worth it to try more or just move to something else, because this seems to not bring so much information. Yeah.
And maybe just because there are different topics among this work, it's the Deep-SDM, if it works or not, and the other topic was whether the plants brings information to the microclimate. And so did you try to just compile other variables about plants in the linear model, just to also check if in the linear model the plants bring something or not based on the same data?
We wanted to. The problem is that you need to find which variable you can provide that have a linear correlation with the microclimate. So the vegetation height has a linear correlation, because in fact if you look at the max and mean, there is an inversion of correlation. So mostly when the vegetation is low, the maximum temperature is higher than in where the vegetation is high, and it's inverted for the minimum temperature, where the minimum goes down more where the vegetation is low and stay higher when the vegetation is high. So we know that we have a relationship that is close to linear for that, but for other indicators it's not clear where you can have some linear or not. And as soon as we try a non-linear model like random forest, XGBoost, even with the same number of variables than the linear model, there it's overfit because it tried to make some too much complex.
Just a question about like spatial extent, because like how big is usually like a unit that is relevant for microclimate?
So it depends on what you are looking for. So here we were looking at the temperature at 5 centimeters above ground. So that means that we were looking at a microclimate that is valuable probably for some small mammals and things like that, or even like ground mammals, like just not the huge mammals, but every mammals and things like that. But if you look for insects or things, sometimes you want to look at parameters that are at even way more smaller scale.
Because I think the slide you showed that you chose observations with an accuracy that is meant to be like around 55 meters, but also I guess you use like sentinel patches that probably cover like a large extent, I guess. So do you think there could be like some smearing, like spatial smearing effects due to this, that maybe it's not able to model the the microclimates because the extents are too large both for the observations and the sentinel patches?
Yes, so I did look at the variable encoded by the model and how they look on the map, and it seems that the resolution is quite hard to really tell, but it's about tenths of meter, like the resolution of the sentinels, because somehow as soon as you just move a little bit the picture, the features that are on the center of the picture or not have different weights, and you can still see. So it's not as precise as the one. So when we were looking this one, this one. This one was with data that are at few meters instead of 10 of meter, but we can really see some sharp edge. Here it was not as clear sharp as here, but still it seems to be quite in the range of what we were trying to do.
So I don't know what the canopy model you use, but most of them that I've seen, they use like a single pixel of sentinel, so maybe like that kind of...
It was a CNN model, so they were using a patch, but they were providing the output at 10 meter resolution.
Thank you very much, Benjamin. So I think that we should move with the next speaker. It's okay for you?
Thanks again.